Have you ever wondered what's really going on when you crank up the heat on a chemical reaction? I mean, we all know it speeds things up, but by how much exactly? Well, today we are cracking that exact code. We're going to walk through a classic chemistry problem, and by the end, you'll have the key to solve it yourself.
It seems like a pretty tough question, right? But the answer is super fascinating. And, even better, it's something we can totally calculate. So, let's find out. Just how much does a little bit of heat actually supercharge a reaction?
So what we're going to do is walk through a very common type of problem, the kind you definitely see on an exam. It's all about something called a first-order reaction, and we're going to look at how its speed changes when the temperature gets a boost.
I like to think of these problems as little detective cases. And what's the first thing any good detective does? You gather the clues, right? So let's break down exactly what we're given to work with here. Okay, here are our clues all laid out. We start at a temperature of 293 Kelvin. At that temp, the initial rate constant, we'll call it K1, is 10 to the minus 3. Then we turn up the heat to 313 Kelvin, and our final rate constant, K2, jumps way up to 10 to the minus 2. So our mission, should we choose to accept it, is to use all this to find the activation energy, or EA. That's basically the minimum energy needed to get this whole reaction started.
Now, the problem makes a point of saying this is a first-order reaction. So what on earth does that mean? Well, it's actually pretty simple. It's just a reaction where the speed depends on the concentration of only one of the ingredients. It's good to know, but the real key to our puzzle is coming up next.
So we have the rates, and we know the temperature changed. But how do we actually connect those two things? We can't just guess. No, we need a special, powerful formula that's designed for this exact situation.
And here it is, the Arrhenius equation. This, my friends, is our master key. I know, it looks a little intimidating at first glance, but let's just break it down. This beautiful formula links our rate constants, K2 and K1, with that activation energy, EA, that we're trying to find. It also uses the universal gas constant, R, and our two temperatures, T1 and T2. It is the perfect tool for the job. All right, here's our plan of attack. We're going to do this in 3 easy steps. First, we'll figure out that rate ratio. Super simple. Second, we'll plug everything we know into our hero equation. And third, we'll solve for our target, EA. Ready? Let's do it.
Okay, step 1. Before we even touch that big equation, let's get the easiest part out of the way. We just need to figure out exactly how much faster the reaction got. To do that, we'll just divide the final rate, K2, by the initial rate, K1.
And would you look at that? We take 10 to the minus 2, divide it by 10 to the minus 3, and we get 10. That's it. The reaction is running 10 times faster than it was before. So that whole K2 over K1 part of our big equation, it's just the number 10. Easy, right?
All right, with our ratio figured out, we are ready for step 2. It is time to take our nice, simple number and all our other clues and plug them right into the Arrhenius equation. Okay, let's plug and chug. The log of our ratio becomes log of 10, which is just 1. We're still looking for EA. R, the gas constant, is always 8.314, so we pop that in, and then we just plug in our temperatures, 313 for T2 and 293 for T1. And just like that, the equation is all set up. Now we just have to solve for EA.
And here we are, the final step, the home stretch. We have all the numbers in their spots. All that's left is a little bit of algebra. We're just going to rearrange the equation a bit to get our target, EA, all by itself. This is the moment of truth.
And after running the numbers, drum roll please, we get our answer, 10.5 kilojoules per mole. That is the activation energy for this reaction. That's the energy hump the molecules had to get over. And we calculated it. Mission accomplished. Awesome, we did it. But you know, getting the right answer is only half the fun. The real win is knowing the strategy so you can do it yourself next time. So, what's the big takeaway for tackling any problem like this one?
Here it is, your battle plan for exams. First, always organize your clues. List what you know, what you need. Second, find your master key, in this case, the Arrhenius equation. Third, just like we did, get that rate ratio calculated early. It makes everything so much simpler. And finally, a pro tip. Watch your units. Make sure you're consistent, follow these steps, and you're going to crush these problems every single time. And that pretty much wraps it up. We have cracked the code for a first-order reaction. But it does leave us with a little something to chew on. What if this wasn't a first-order reaction? What if the problem said it was a zero-order reaction, where the rate doesn't depend on concentration at all? How would that change things? Something to think about. Thanks for joining me.